This time we're going to be talking about vectors. Here we can see a reference to Wolfram and Maths World, and a little diagram here. I'm not going to refer to a lot of this because a lot of this is beyond where we need to take this presentation. A vector is a quantity that has both a size, magnitude, and a direction. So at school you will meet certain quantities, possibly in physics, that are referred to as vector quantities, and in other words you can quote a size for them, but a direction is also needed. Velocity is a vector, so it needs a size, but it also needs a direction. Speed, however, isn't a vector, and what we tend to call things that are not vectors are scalar quantities. So mass would be a scalar quantity because a direction doesn't have to be specified. So let's look at some properties of vectors. First of all, you will probably have met them at GCSE in the context of transformations. Let's look here. Here's a vector being represented by means of a translation. A translation, if you recall, is where you take a shape and you slide it somewhere. Now this little line segment represents the vector, and as you can see, as I move that, the image is being translated. Now one of the first things you need to get to grips with vectors is they don't have to be fixed anywhere in space. This vector here, if I just grab it and move it, you can see that that vector, I could place it anywhere on the screen. What it's doing is taking every one of the points of this object shape and translating it to a corresponding image point over here. And if we look over here, you can see the notation for this vector, and this is where you very often first meet vectors. The 4, 1 represents a move 4 in the x direction followed by a 1 in the y. Not necessarily followed by, but 4 across and 1 up. And this is one way of specifying vectors as 2 perpendicular movements, or the result of 2 perpendicular movements. And you might say, well, didn't you specify a direction? Well, yes, another way of representing a vector could be a size and a direction. So I could have specified this vector by its length, and we would work out its length by squaring the 4, squaring the 1, adding them together and square rooting. So an application of Pythagoras' theorem would find the size of the vector or its magnitude, but we'll come back to that shortly. So I could specify with this length and a bearing. So for example, this angle here, which I could find by using trigonometry. So let's go through some questions and we'll pull out some properties of vectors as we go along. So we have a point in space 1, 3 and another point 6, 9. I don't need to plot them, it's just a little diagram to illustrate how we evaluate and find vectors. So here we've got 2 points, 1, 3 and 6, 9. Now the vector AB, the first thing we need to know about vectors is they have to have a direction specified. And this is the vector that takes us from point A to point B. Now we could very easily see that the vector AB is a translation 5 across and 6 up. So we would write that as the column vector 5, 6. Look at the notation. Putting a line across the top AB means it's the vector that takes you from point A to point B. BC this time. Let's put it down here. So let's put point C down here. So the vector BC is represented by this line here. Again, this isn't a scale diagram. If I was going to do it accurately, I would plot these on coordinates. It's just for the sake of an illustration. So this vector BC is the vector that takes us from point B to point C. So if you see, we've gone back 1 and we've gone down 12. Direction is important. A to C, well, we can see A and C are already drawn in. The vector AC is illustrated there, and it's to go from 1, 3 to 5, 3. So AC is 4 minus 6. So we have three vectors that represents a move, if you like, from A to B, B to C, or alternatively A to C. So let's look at part B, and that brings out another point that we can illustrate. To go from A to B, followed by going from B to C, will give us 5, 6, a translation 5 across and 6 up, followed by a translation 1 to the left and 12 down. That gives us a column vector 4 minus 6, and you can see that's the same as AC. So what can we say? We can say that AB added to BC equals AC. It doesn't matter the route you will take through a diagram. If you've got representations of each of the translations from one point to a next, if you daisy chain them all together, then the result you get is the vector that takes you from the very start point to your very end point. We can illustrate that more formally with the following law. Here we go. This is often referred to as a triangle law for vector addition. Notice it's vector addition because we've got directions involved as well. If it was just ordinary scalar number addition, then that's a different matter entirely. So A to B plus B to C is the same as A to C. And notice here we've got some other notation. Often, rather than referring to a vector as the translation between 2 points and using this capital letter and arrow notation, often the vectors themselves are just given a little letter. And notice in printed work that's written in bold. What we do in practice, if we were doing the same in written work, is we'd put a line underneath everything that we represent as a vector, and then that shows that we know it's a vector and not a scalar quantity. Extending this idea, we've got what's called the parallelogram law of vector addition, and feel free to pause the video whilst you read what's on the screen. That's perfectly fine. But what can we see here? Look, we've got a vector here, P to Q, and then the vector Q to R, represented by little a and little b. So PR, we could say, is little a plus little b. But if it's a parallelogram, then the vector P to S is the same length and the same direction as the vector Q to R. So here brings out another property, that if vectors have the same size and they're in the same direction, then they're equal. They don't have to necessarily start at the same place, but if they're oriented the same and they have the same length, then they are equal vectors. So we could get from P to R by going up here, P to S and S to R. And for the same reasoning, this edge up here has the vector little a. Some more notation we need. When you combine vectors, what you have is a resultant. So in these diagrams here, the top one, we could say that vector C is the resultant of these other two vectors added together. If you do A-level and you pick up a module like mechanics, or also if you do physics, then you might be working with forces, the resultant of several forces acting on something. Then what you're finding is the overall force that's maybe causing an object to move, or the overall forces that are stopping something from moving. So this word resultant is just a vector context for the sum of several vectors. So let's pick up that idea and have a look at the next few questions. Work out the magnitude. Well, Well, the magnitude of a vector is its size. Some more notation here. Often you will see vertical lines drawn around the side of a vector, and that denotes its magnitude or its size. So if you have vector little a, which is represented by a horizontal move of 5 and a vertical move of 12, again these are not to scale, it's just to illustrate a point. So the vector is, if you like, the hypotenuse of a little right angled triangle. Then the magnitude is clearly an application of Pythagoras' theorem. So vector little a, the magnitude of vector little a is the square root of 5 squared add 12 squared. The numbers are easy here, it's a triple, so that gives us square root of 169, which is 13. So the vector that's represented by the column vector 5, 12 has a magnitude of 13. Let's have a look at B. B is another triple. It's the same triple, isn't it? We'll do without the diagram this time. It's the square root of 12 squared and minus 5 squared. If you're doing this on your calculator, remember to put brackets around the minus 5, otherwise your calculator will simply follow the BIDMAS rules that it's programmed to do, and it will square the 5, but it will preserve the minus, and it will be doing the square root of 144 minus 25, which will lead to the wrong magnitude. Again, this is 169, which is also 13. If we drew the diagram, it represents a horizontal move of 12 and a vertical move of 5. So, regardless of the rubbish drawing, that magnitude is the same as this magnitude over here. Magnitude of C, well, we want the square root of 1 squared plus 3 squared, which is the square root of 10, which we could work out, but up here it says answers may be left as surds. Remember, surds are exact. If it's not a square number in here, then you're going to lead to an irrational number that needs rounding. Magnitude of D, square root of minus 5 squared plus minus 7 squared, minus 5 squared and minus 7 squared, square root of 25 plus 49, which is root 74. Doing this on your calculator will simplify that. If you've got your calculator set to maths input output mode, it will leave it in surd form, and it will also simplify the surds if they will simplify. Part E, the magnitude of the vector AB. Remember, this just means the vector, if you had points A and B, this would represent the translation to get from point A to point B, but we're just dealing with vectors without reference to a diagram at the moment. So it's the square root of 8 plus, the square of 8 plus the square of 15 minus 15 is root 289, which happens to be 17. And the last one, magnitude of PQ, is square root of negative 8 squared plus 4 squared, which is root 80, which is root 16 root 5, which is 4 root 5. In a triangle ABC, A to B, the vector AB is minus 20 minus 15, and vector AC is 24 minus 7. And then it says work out the length of the side AB. So if the vector AB is to go from corner or vertex A to vertex B, then the magnitude of the vector AB is the length of the side AB. So it's perfectly acceptable to use this notation because we know that we're talking about the length of a side AB. So it's square root of minus 20 squared plus minus 15 squared, which is a square root of 400 plus 225, which is 625. Square number, so the side is 25. AC, side AC, we have 24 squared added to negative 7 squared, which is a square root of 576 plus 49, which is 625, which equals 25. Part B says show that the triangle is isosceles. Well, that's shown that two of the sides are the same. We really ought to go ahead and see if the third side is the same. So let's just do a little sketch. It's not, there's no axes, and so it's possibly orientated incorrectly, but we've got A, we've got B, and we've got C. Vector AB we know, vector AC we know. So if we wanted to find vector BC in order to then find the length of its side, we use the triangle law of vector addition. So BC will be, and this brings out a point I hadn't mentioned earlier, if you move through, if you use the vector in the reverse direction to the way it is being defined, then the magnitude is the same, the direction is completely reversed. So vector BA has the same magnitude as vector AB, but all of the signs are inverted. So that will be BA added to AC. Vector BA is therefore 20, 15, same magnitude as AB, but in the reverse direction. Vector AC was given 24, negative 7. So the vector BC would be 44 and 8. So length BC, well, we're getting to the point where we can see that this is clearly not going to give 25, but let's just finish it off anyway. The magnitude of BC would be 44 squared plus the 8 squared, which would give us 2000, which is 20 root 5. So we've shown there that the triangle is isosceles. We could have stopped here, really, but this illustrated the triangle law as well as showing that it is isosceles. Okay, so we've got some questions here that use vector addition. Why not pause it here and try these calculations for yourself? Okay, welcome back. Those are the answers, if you want to compare what you did with the answers here. Let's move on then to other aspects of vectors. So that's been the numerical aspect of it, and let's just recap. Column vectors can represent a translation. They can represent just a vector as it is. If you combine vectors, then the sum of the vectors, you simply combine the top component, the x part, and you combine the y part separately. The magnitude of a vector, we use Pythagoras' theorem, and that finds its size, its length. Another aspect of the vectors that you're likely to encounter is vector algebra. Coupling it with geometry and some diagrams and a little bit of background knowledge, we can use vectors to prove things, we can use vectors to illustrate things. Let's look at this question here. It's a regular hexagon, so we know that all its sides are the same length. We know that all its angles are the same. What else are we told? We're told that from A to B can be represented by the vector little n. And from what we've said earlier, if vectors are parallel and the same length, then they are equal vectors. So answer A is very simple. ED is vector little n because it's parallel. AB and ED are parallel and the same length. So AB, vector AB, is equal to vector ED. We've given more information that BC is M and CD is P. So we've actually got enough information now to define any starting point, any vector to get from anywhere, any point around the edge to any other point around the edge. And the way we do that in vector questions like this is you find a route through the diagram that has vectors defined that you know about. So for example, A to C, we don't have any information about going directly, but using the triangle law, we know that A to C is the same as going from A to B followed by B to C. And those are already defined as n plus m. Numerically, this was just like the previous questions you had a go at. This vector and this vector could have been defined numerically, and that's all you were doing. Now we're just leaving it in an algebraic form. Vector AD. As you work through questions like this, there will often be more than one route that opens up that you could take. But the fact remains that if the start point and the destination are the same, however many legs, steps, paths through the diagram you take, providing you make no numerical errors, the answer will be the same. So from A to D, we could go from A to C, because we now know it, and then just go from C to D. A to C was our previous answer, so it's n plus m, and then C to D is P. What is FD? Well, let's have a look at FD. Bit of an open-ended question there, but what it's getting at is what geometrically can you conclude about FD? Well, F to D, let's see. We could go all the way around the outside from F through A, B, C and D, or from F to A and then A to C or A to D, because we now know those. The only one that apparently looks like we don't know it is FA. But because this edge is parallel to CD, which is defined, we know its magnitude is the magnitude of P. So we can put that P is that vector. So if we want to go F to A, we know the magnitude, but it's in the reverse direction to the definition of that edge. And then let's just go FA plus A to D. You could pause it and convince yourself that the answer will be the same whichever route you take, but let's just carry on with this. F to A is the reverse direction to the vector P, and then AD was our previous answer, n plus m plus P. Now this one will need simplifying because we've got a negative P and a positive P, so we get n plus m. So there, we've got the vector representation of FD. So what is FD? Well, we can see by comparing that and that, we can see that FD, the vector FD, is parallel to AC and equal in size. So in other words, vector FD equals vector AC. And you might recall that anyway from your geometry of regular polygons. But this has shown it in a vector algebra form. Moving on then, a little bit more notation. We can have vectors that represent a translation from one point to another, and we can have algebraic vectors. One vector that is referenced to the origin is referred to as a position vector. If we have a point, let's call it the point A just for the fact that that's what it mentions here. If we've got a point A, and say it's got coordinates 3, 7, then that means relative to the origin, OA, the vector to get from O to A, would be 3, 7. And that will be referred to as a position vector. So it's very easy to turn a point's coordinates into its position vector. Another one, B 3 0 OB would be 3 0. Scalars I've already referred to. A scalar quantity is a non-vector quantity, it's an ordinary number in other words. We can multiply a vector by a scalar. You also need, well, you don't need to know, but you can multiply vectors together, but that's another story that we're not dealing with at the moment. Let's have a look at another question that deals with vectors being scaled up by a scalar. 5m, and again feel free to pause the presentation if you want to try some of these yourself. 5m, the 5 is the scalar, m is the vector, so that means 5 lots of the vector 4, 3, which is 20 and 15. You could compare it to multiplying out a bracket. When you're dealing with algebraic expressions in general, the number outside the bracket gets multiplied by everything in the bracket. Here, we're sort of absorbing the scalar quantity into the bracket because we still want our answer to be a vector. So that's 5m minus 2 lots of n is minus 2 lots of 6 minus 3, which gives us the vector negative 12 and positive 6. 4m add 3p is 4 lots of 4, 3 add 3 lots of minus 2, 6, which would be 16, 12 added to minus 6, 18, which in turn is 10, 30. 2m, take away 4n, add 5p is 2 lots of 4, 3, take away 4 lots of 6 minus 3, add 5 lots of minus 2, 6, which is 8, 6. Take away 24, negative 12, add negative 10, 30. Where you put the negatives is up to you, as long as you preserve them where they should be preserved and you obey your directed numbers rules. So 8, take away 24, add minus 10 is minus 26. 6, take away minus 12, add 30, 48. Done. The magnitude of the vector m. Magnitude of m, if you recall, Pythagoras theorem application, 4 squared add 3 squared, triple again, square root of 25 is 5. Magnitude of 2m take away p. Well, we need to find that out first. What we mustn't do is just take the magnitude of m and take away the magnitude of p from it. We need the magnitude of that as a single column vector, so that's what we need to evaluate first. So 2m is 8, 6, because we've done that before, previously. Take away p, so we're taking away negative 2, 6. The vector itself is therefore 10, 0. And there isn't a great deal of work to do here to see its magnitude. 2m take away p, A vector just in one direction, either horizontally or vertically, its magnitude is just that number, isn't it? So it's 10. So we have the points P, Q, R and S. They have coordinates -2, 5, 3, 1, -6, -9, and 14, -25. Position vector of OP. Recall, the position vector is simply its coordinates turned into a vector. So that's -2, 5. Write as a column vector PQ. PQ is to go from -2, 5 to 3, 1. So we have increased it by 5 in the x direction, decreased it by 4 in the y direction. And RS is to go from point R, -6, -9, to point S, 14, -25. That's an increase of 20 in the x direction, decrease of 16 in the y. What do these results show about the lines PQ and RS? Well, look, there's PQ, there's RS. What can we see? Well, we can see that RS is a scalar multiple of PQ. It's 4 lots of it. So the results show that PQ, vector PQ and vector RS are parallel. And we've already stated it there. RS is 4 times length of PQ. So vectors that are multiples of each other are parallel, and then the scalar multiple tells you how many times bigger they are. The point A has coordinates 1, 3, B 4, 5, and C -2, -4. Find the coordinates of another point D where the vector CD is 6 lots of the vector AB. So our first job is to find the vector AB, and that's the vector that would take us from the point A to the point B, which is 3 to the right and 2 up, which therefore means that CD is 6 lots of this vector, which is 18, 12. So to get from C to D, we add on 18 to its x coordinate and add on 12 to its y coordinate. So starting at -2, -4, doing what we've just said, add 18 onto its x coordinate, and that gives us 16. Add 12 onto its y coordinate, that gives us 8. So D has coordinates 16, 8. Let's just do that in a vector fashion. Here's O, here is C, here is D. So OC, the vector OC, we know is -2, -4, because its coordinates are -2, -4, so its position vector is -2, -4. What we're asking for is its coordinates, so we could look for this position vector. We know the vector CD is 18, 12. So using the triangle law, OD is OC added to CD, which is -2, -4 added to 18, 12. You can see it's exactly the same calculation we did above, just in a vector fashion, and that gives us 16, 8, and same result, therefore D is 16, 8. two ways of doing the same thing. And again, feel free to pause it if you want to try these yourself before we go through them. Regular hexagon again, it's a common one. So A to B is M. FC, we're told, is parallel to AB and twice as long. So here we go. F to C is 2M. It's parallel, so it's a multiple of M, and it's twice as long. So we've answered it. F to C is 2M. Express F to D in terms of M and N when we know that this vector C to D is little n. So FD let's use what we've already got. It's F to C added to CD. So it's 2M add n. BC is the vector x. Express AC in terms of M and X. So A to C is the same as A to B add B to C M plus X. The lines AC and FD are parallel and equal in length. Find an expression for x in terms of m and n. Well, we have an expression for AC. That was the answer that we've just done. We have an expression for FD. That was what we've just done here. If they're parallel and equal in length, that's the condition for equal vectors. So that means that m add x, this one here, must equal 2m add n, this one here. We're looking for an expression for x in terms of everything n, else we rearrange a vector equation the same as we do any linear equation by adding and subtracting. So let's subtract an m, but it's a vector we're subtracting, so x equals m add n. A variation on the vector algebra question is one where you have points that are part way along a side, so we have to adapt previous parts of the question in order to find new answers. So let's have a look here. The vector AB, A to B can't be determined directly, so we go along the diagram via routes that we know about. So A to B is AO added to OB. AO is negative A, OB is B. So minus A add B. Also we could write that as B, take away A. They are comparable. P is the midpoint, so AP is a half of AB. So this is a half of brackets B take away A, which we could leave as that or write separately as half B take away half A. So OP, the position vector if you like, of P would be OA plus AP. Vector questions like this very much rely on previous parts of the question, so don't start all over. Use what you have previously done that's useful. So what we have here is a half of A add a half of B. So here we have a parallelogram. And the result from question 3 is what we've just worked out, that the midpoint is, so OP we can state, because that's what we've just worked out, is a half of A added to a half of B. So P is there somewhere. Express OC in terms of A and B. So OC is O to A added to A to C. Well, O to A is defined as A. A to C is parallel to OB, so it is B. Q is the midpoint of OC, so let's put that in. Now, you can see from the diagram it's going to be the same place, but what we have to assume is that we don't know that just yet. And we'll show it algebraically. Q to O is a half of C to O, because it's the midpoint. So it's a half of, well, we've worked out OC, CO is same magnitude, opposite direction, minus a half A minus a half B. Hopefully you're getting the idea of this. What do your answers to A and C show about the points P and Q? Well, OP, let's see, OP is half A add a half B. OQ is half A add a half B. So we can say straight away the parallel and same magnitude, but we can say something more because they both start at the same point. They're the vector to go from O to P and O to Q. So they're parallel and the same magnitude, but because they're both position vectors, P and Q are the same point. What property of a parallelogram has been proved? Well, if P is the midpoint of OC, P is the midpoint of AB and Q is the midpoint of OC and they're in the same place, what we've actually shown is that the diagonals are bisecting each other. So that's a mixture of all the different sorts of questions that you like to meet at GCSE. Might touch a little bit on some of the AS vector work that you're likely to meet. Doesn't go as far as what you'll meet in further maths. It is quite an expansive topic, and we've really just touched on it here for the benefits of those doing GCSE. So I hope that's been useful. Let's just recap what we've talked about. Vectors have a size, which we've called magnitude, and they have a direction. They can be defined as that magnitude and a direction, which could be a bearing. They can be defined as a column vector, which is made up of a horizontal part and a vertical part. Those parts are called components. We can add vectors together, and to do that we add them in column vector form, and the horizontal components are added and the vertical components are added. When you add vectors together, what you get is called the resultant vector. We can add as many vectors as we want, but if the beginning and the end are in the same place, the route through a diagram doesn't matter. If we can scale a vector up by a number, non-vector numbers are called scalars. Position vectors are vectors relative to an origin. The magnitude of a vector can be determined from its column vector format by using Pythagoras' theorem. We can use vectors in algebraic form on diagrams to prove geometrical results. And I think that's it. So I hope you found that useful. Thanks for listening. Come back again. Bye.